Hi folks, thanks for attending our presentation. My name is Alex Wazine, and today I'll be one of the four speakers giving an overview of the scientific and technical aspects of the Violet Space Weather Exploration Mission. So, the Canadian CubeSat project is a project being run by the Canadian Space Agency, providing post-secondary institutions with a very unique opportunity of designing and building their own small satellite called a CubeSat, while simultaneously inspiring and training the next generation of space researchers in Canada. So Violet is a 2U CubeSat being designed, built, and tested by the CubeSat NB, which is a joint venture between the New Brunswick Community College in St. John, the Université de Moncton, and the University of New Brunswick. And CubeSat NB is one of 15 other teams across Canada that are part of this Canadian CubeSat project. So, Violet has two scientific payloads on board making observations of phenomena linked to the electron content of the ionosphere. And the first of these is the GNSS receiver for ionospheric and position studies, or GRIPS for short, which is observing radio signals whose propagation velocity is related to the total electron content it's passing through. The other payload is the Spectral Airglow Structure Imager, or SASI for short. SASI will be imaging the oxygen red line airglow at approximately 240 kilometers above the Earth's surface, and the brightness of this airglow is modulated by the electron concentration. So together, the two payloads provide a complementary means to monitor the electron content of the ionosphere, as well as the ionospheric conditions. So the brightness of the red line emission varies heavily with solar activity and geomagnetic and atmospheric phenomena, and pairing the SASI and GRIPS observations allows wave features such as traveling ionospheric disturbances, plasma bubbles, and auroral signatures to be observed. So on its own, the GRIPS observations complement these from the European Space Agency's SWARM mission, and they could even be combined with terrestrial observations in a tomographic analysis. And SASI's observations will also complement the observations by NASA's recently launched ICON satellite. And SASI even has the potential to record redline observations further poleward of those provided by ICON. So currently, the GRIPS payload's main mission is to provide insight into the behavior of the Earth's ionosphere and provide real-time position, velocity, and time estimates, as well as the total electron content. So the GRIPS payload will be logging its data at 100 Hertz, and it's going to get approximately 500 megabytes of data per orbit with a target of at least one orbit per day. And while it's logging, it will be tracking the GNSS constellation signals of GPS, Galileo, GLONASS, and Beidou on the L1, L2, L5, and L6 frequencies. And on the other end, SASI will be imaging the oxygen redline airglow in the upper atmosphere, which is approximately the 630 nanometer band. And the problem with imaging at this band is that the airglow is very faint at approximately 223 photons per second per pixel. And so this requires longer exposure times. And because we have longer exposure times, there's a need for further processing of the images to be done on the ground before you can extract the necessary scientific data from it. And so SASI's optics that it's using is a Schmidt-Weisshaller reflector system, and this is because the CubeSat is very limited when it comes to space, so it has to be in a 10 by 10 by 5 centimeter block for all the optics. So it's very crunched in there. So as I said earlier, the image processing has to be done on the images before they're usable. And this is because when SASI is taking images, there's a longer exposure time. And during its exposure time, there's going to be factors like linear motion and rotational motion, which will significantly blur the images. So, and methods for reducing the blur in the images are currently being explored by the team, and the most significant of these methods would be modeling the motion of Violet during the exposure time with a combination of the attitude determination and control system and the GRIPS instrument. This could be done by grabbing the exact position and roll and rotation rates of the satellite at the start of an exposure and at the end of an exposure to see the difference between the two, and building a blur kernel from this information. And then this blur kernel can be used in the recovery of the image. I'm going to now pass you on to Alex DiTommaso, who's going to take care of the structure and the mechanical side of the project.
Hello, my name is Alex DiTommaso, and I'll be sharing the overall design of Violet, as well as the experimental attitude determination and control system design. The main approach taken for the mechanical design of Violet was to be a modular system to ensure the spacecraft can be easily disassembled and assembled relatively easily. Violet includes 3 modules: the plus Z, minus Z, and center module. Starting from the minus Z module, we have the GNSS antenna, the GRIPS payload, the onboard computer, the software-defined radio, the VHF and UHF board, the linear microwave board, the ADCS control board, the ADCS Z-torquer board, the SASE control board, the EPS system, and finally the SASE optical assembly. The SASE payload is designed to image the Earth's ionospheric airglow layer. To do this, its imaging axis must be oriented minus 12 degrees relative to the surface of the Earth. PMAX systems make a spacecraft act as a compass, pointing north-south and following the Earth's magnetic field lines throughout its orbit, allowing for imaging only where the magnetic inclination is minus 12 degrees plus or minus pointing error. The development of the hybrid magnetic attitude control system allows for more options for imaging across a wider range of latitudes. By using passive and active magnetic components together, the spacecraft's magnetic dipole can be offset, allowing for different attitude settings. A side view of an ideal attitude for SASE imaging can be seen in Figure 2. The requirements which drive the development of the subsystem mainly come from the SASE payload, as without an imager, Violet would only require a passive system to ensure stable flight. The main requirements for the HMAX system include a post-deployment settling time or detumble of less than 7 days, steady state roll rates less than 1.5 degrees per second per axis, steady state precession rate less than 2 degrees per second, and a steady state precession angle less than 10 degrees. Lastly, after HMAC actuation to a new attitude, the spacecraft must reach steady state within 8 hours or roughly 5 orbits. The hybrid magnetic attitude control system includes a pair of magnetic torque coils on the X and Y axes and one coil aligned with the Z axis with a max power of 0.25 amp-meter squared per axis. Additionally, the system includes a 1 amp-meter squared permanent magnet and HYMU 80 hysteresis rods aligned with the X and Y axes. Magnetic dipoles created orthogonal to the permanent magnet will result in an angular offset or beta angle of the magnetic dipole relative to the Z-axis of the spacecraft. A Kalman filter will be utilized to accomplish sensor fusion from the gyro, sun sensor, and magnetic field lookup table data. The first results to be analyzed in this is the detumble phase of simulation, for which the satellite axes relative to the geomagnetic field vector are plotted using the MATLAB toolbox, the Smart Nano Satellite Attitude Propagator. The roll axis is the most critical response plot to analyze, as it is the imaging axis as well as the principal magnetic moment axis. The mean and median of the roll axis data upon reaching steady state was found to be 25.6 and 13.5 degrees respectively. This gives some useful information, as the conclusion can be made that there is still some unwanted oscillation present in the system as the spacecraft tracks the local geomagnetic field vector. Modifications will be made in future simulations to further optimize the damping of the system. Snap simulations were then run to better understand what the response to the system is when the magnetic torque coils are powered, specifically to see the trade-off between higher beta angles and stability. Actuation of the yaw torque coil to 50% power occurred at the 16-hour mark, denoted by the red lines there in the plot to the right. Once the torque coils were powered, a short transient phase of stabilization occurs over 3 to 5 orbits as the system reaches stability. Once stable, the mean and median beta angles were found to be 19.8 and 20.4 degrees respectively. This result is expected as the beta angle increases as a function of magnetic dipole moment strength in the orthogonal axes. Thank you.
Hello, my name is Sarah Siddika. I'm going to talk about communication system in Violet mission. Violet requires high data rate to transfer the large mission data volume. As a result, frequency in S-band will be utilized. Frequencies that are requested from International Amateur Radio Union is 2.45 GHz for transmission and 2.433 GHz for reception. These frequencies are not commonly used by the amateur radio operator in Fredericton area, so we expect minimal interference from the surroundings. The bandwidth of 2 MHz has been requested for downlink. The bandwidth will be used to downlink 350 MB and 500 MB data that SASE and CRIPS payload generate per orbit. This functionality will be provided by S-band unit, which consists of SDR, communication platform SCP, linear microwave board LMB, and S-band antenna, where the S-band antenna is in-house field microstrip dipole to have omnidirectional radiation pattern. SDR communication platform SCP consists of two devices, a software-defined radio SDR which connects to LMB and a Linux computer which connects to the rest of the satellite. This consideration of SCP is that the range between Violet and the ground station vary the data throughput on each pass, which also causes to vary the received signal to noise ratio. A 14 dB of variation has been observed from initial simulation. To overcome this challenge, adaptive coded modulation has been developed by a team member. This will adjust the current constellation being used by the transmitter based on channel state information obtained through the return channel. Additionally, new constellation will include novel constellations that contain number of points that are not power of 2 and also not divisible by 2. An example would be 3 PSK or 5 PSK. The new constellation will increase the throughput of the system. Fractional bit per symbol will be created as a result of using non-power of 2 constellation points. To combat this, the current design will implement a method of observing a specified number of waveforms to obtain a number of bits that is close to an integer number of bits. This will help to maximize the efficiency of fractional bits per symbol system. Linear microwave board, in short LMB, is a half-duplex multi-stage linear amplifier system used for both transmission and reception. LMB interfaces with software-defined radio communication platform and antenna system. The system is designed to boost power up to EIRP limit. The amplification of signal aids to establish better communication link between CubeSat and ground station at the requirement of SNR and data rate in this band. The transition from transmit to receive channel is negotiated between SCP and LMB. The three-stage gallium arsenide and gallium nitride combination of power amplifiers achieves around 45.5 dB gain at nominal temperature according to the simulation. Amplifiers are designed to operate with power backup technique from saturation point so that it maintains the linearity. But it comes at the expense of efficiency. The operation in power backup leads to 20 to 25% efficiency. The third stage gallium nitride amplifier needs external biasing and a proper biasing sequencing. This requirement is being ensured by a bias sequencing circuit. A dual feedback temperature compensation circuit is being investigated, which tracks the quiescent drain current required to automatically control the gate voltage. The stability of amplifier stage was analyzed with Rowlett's criteria for unconditional stability. The K and delta factors are defined from S parameter of the devices. LMB is a heat source in CubeSat due to gallium nitride amplifier efficiency and power requirement. Passive thermal control methods, mostly based on thermal straps, are possible heat control solutions. S-band communication system will use antennas placed on the spaces between solar panels on 4 sides of the CubeSat. Each of these antennas will use printed monopole design. Such a design is required because satellite is free to rotate about z-axis, meaning that the side facing the Earth changes as the satellite rotates. This means that the antenna's radiation pattern must be close to omnidirectional, resulting in low gain values. Antennas will be used for both uplink and downlink for S-band, thus must have a good impedance match and radiation properties at both frequency. A design for center frequency at 2420.5 MHz and a bandwidth of 35 MHz should serve to meet the link budget requirements. An additional constraint placed upon the S-band antenna is their mounting position. Due to where the solar panels are relative to the proposed design, antennas must contend with surrounding ground planes, which complicate the design by distorting the gain pattern. Because the grounding is different on one of the faces, this leads to additional problem with asymmetry. Thank you.
Hello, my name is Ben Wedemeyer. Violet software starts with the free RTOS operating system and CubeSat Space Protocol, CSP, running the onboard computer. CSP is a network and transport layer protocol and allows for simplified connectivity between the distributed embedded systems on Violet. CSP is similar to the TCP/IP network stack, but is connectionless. This is an overview of the modes of operation of the onboard computer on Violet. Failure mode is a mode that is triggered when a fault is detected by the satellite's fault identification system. Calibration and maintenance mode is a mode that provides the required calibration and maintenance services to the mission subsystems. Manual mode is a mode that is triggered manually by a command from the ground station. This mode is used to control the satellite manually via a set of predefined commands. And finally, normal mode is the primary mode in which the satellite operates when it is healthy. This mode implements an infinite loop, a succession of tasks that meets the objectives and requirements of the mission. The software of Violet is written in C to allow low-level and energy-efficient software implementations. To ensure software safety, we follow the Power of 10 rules from NASA/JPL for reliable software. Where data needs to be encrypted, we follow the guidelines from the American National Institute of Standards and Technology to improve data and system security. Because hardware development is still underway, we had to find a way to test low-level software without the actual hardware. To achieve this, we designed our own simulation framework that is capable of simulating the power supply, CAN buses, and communication between the ground station and the satellite. Thanks to the software simulation, we can design, implement, and test the actual code for the satellite without access to the hardware. Finally, Violet is currently in the critical design phase. Flat set development and testing is underway, and the development and manufacturing of engineering models is also occurring. Our tentative launch date is summer 2022, and Violet will be deployed from the ISS by a NanoRacks CubeSat deployer. Thank you.